Hi, welcome back to Mrs. Thompson's classroom today. We are going to look at how to solve inequalities. So first of all, we're going to talk about a little vocabulary, learning how to describe these inequalities. Then we're going to solve them and write our solutions in both set builder and interval notation, which you've seen in an earlier video of mine. And we're going to draw our solutions on a number line so that we can get a visual of what these look like, because they are sets of infinite numbers. So let's do some vocabulary. First of all, a conditional equation has at least one solution. Okay, but that also means it has a number, has at least one number that is not a solution. Okay, so we may have an infinite number of solutions, like it might be everything between 1 and 10. That includes all the decimals, all the fractions, anything you can think of between 1 and 10. But there has to be something that is not a solution. So we're not talking all reals. If we have one that has all reals as a solution, then we're talking an identity, which is always true. Okay, so this means that its solution is all reals. Okay. Now, the other thing that can happen is we have no solution. And we call those inconsistent. Just like with our equations, if the equation didn't have a solution, then it was inconsistent. Okay. And equivalent inequalities have identical solution sets. Okay, so those are the different types of inequalities we can have. Let's get started with our first example. Well, actually, let's just take that back. We want to do a little investigation first. Because with inequalities, we can do all the same things that we do with equations. We can add to both sides. We might have the distributive property going on. We can multiply and divide to both sides, but there's something interesting that happens when we do that. So on this number line, I can see the numbers 5 and 8, and it is obvious that 5 is less than 8. Okay? Now, if I wanted to take this inequality and multiply it by -1 on both sides, now I get -5 and -8. So if I put those on a number line, what happens? They have switched places. -8 is further to the left. That means -8 is less than -5. So we notice that when I multiply by that negative, it flips the inequality. So we have to be very careful when we're doing multiplication or division. If we multiply or divide by a negative, the inequality is going to change directions. Okay, now let's get to our first example. So we have an inequality with one variable, just x. So I'm going to start just like I would with an equation, and I'm going to distribute the 2. So I get 2x plus 6 is greater than 5x minus 12. Okay, now the objective is to get the x by itself. So I'm going to combine the x's. So I'll do minus 5x. And I get -3x plus 6 greater than -12. Then I'm going to subtract the 6 from the -12. And I get -3x is greater than -18. And now I need to divide by -3, which is the same thing as multiplying by -1/3. And so in doing so, I'm left with an x, and I'm left with a 6. But because this was negative, I'm going to flip the inequality around. So this is my solution. To write it in set builder, okay, set builder, I will put the brackets around it, and this reads x such that x is less than 6. To write it in a interval notation, if I'm less than 6, I'm going to go everything to the left of 6. So I'm going to go from negative infinity to 6. And I use a parentheses because I'm not equal to 6. On a number line, put my 6 on here. I'm going to start at 6, but not equal it. So I put an open hole there, and I go to the left. And that's my solution on the number line. Okay, now let's do this one. Again, I'm going to start by distributing the 2. I'm going to combine my like terms here. So this gives me 2x minus 3. I need to get the x's together. I notice I have 2x on both sides. So when I try to get them together by subtracting 2x, I notice they cancel on both sides. And I'm left with 1 is greater than or equal to negative 3. Well, this is false. Or is it true? That's the question. So if I look on a number line, 1 is greater than negative 3, so this is always true. So that makes my solution all reals. So I can write it in interval notation, or I can write it in set builder notation. And of course, the solution on the number line is just the entire number line. Okay, let's do one more. Now this one includes 2 different inequalities, but this word or in between them makes it what we call a disjunction. Now the word or implies that only one of these 2 things would have to be true. They could both be true, or one of them could be true. The only way that it becomes false is if they are both false. Okay, so we're going to have to solve each of them individually. So I'm going to subtract the 1, and I get 2x less than 4. Divide by the 2, and I get x less than 2. Over here, I'm going to add the 3, and I get x is greater than or equal to 11. Okay, so on a number line, let's put a 2 and an 11. To go less than 2, I'm going to start at 2 and go to the left. So less is left. And then I'm going to do x greater than or equal to 11. I'm going to start at the 11, and I'm going to go to the right. Now notice I put an open circle on the 2 because it can't equal it. I put a closed circle on the 11 because it can. So in set builder, I'm just going to write the inequalities. In the interval notation, to go less than 2, I'm going to go everywhere to the left. So the negative infinity is as small as we can get, so it always goes on the left-hand side in the interval. And then I'm going to join this with x greater than 11, and I want to make sure I put a square bracket because it can equal the 11. Okay, now that's a disjunction, an or statement, but we can also have conjunctions, which are and statements. But I'm still going to solve each of them individually. So distributing this will give me 4x plus 4 is greater than or equal to 12. Subtracting 4 gives me 4x is greater than or equal to 8, which makes x greater than or equal to 2. On the second one, I'm going to add 1. I get 3x less than or equal to 15, so that gets me x less than or equal to 5. So on a number line, I put a 2 here and a 5 here. I want to be greater than or equal to 2, and I want to be less than or equal to 5. And notice that makes me going in both directions forever. However, the and, unlike the or, the and implies they both have to be true at the same time. So that means I'm only doing where they overlap. So my final solution would be this red line. And I put dots on the end, filled in dots, because I can equal it on both sides. That would make my solution between 2 and 5, or in interval notation from 2 to 5. Okay, let's do one more example. I'm going to erase a little bit of this. And do this one. Now this is also a conjunction. The implication is that this is an and statement. So I need 0 less than or equal to 3x plus 2. And 3x plus 2 is less than or equal to 5. Okay, so I need to take this, and this 2 that I want to subtract is going to end up being subtracted from the 3x plus 2, but it's also going to subtract from the 0, and it's going to subtract from the 5. So you can do it still written together, or you can split it apart. So I end up with negative 2 is less than or equal to 3x, which means negative 2/3 is less than or equal to x. Over here, I get 3x less than or equal to 3, so x is less than or equal to 1. So if I put this on a number line, again, I'm going to put dots because I can equal. I want to be greater than the negative 2/3. I want to be less than the 1, so we're coming towards each other. Again, this is a conjunction, and it is an and statement. So my solution set would be x between 2/3 and 1, or I can write the interval. Okay? All right. Now, we also can do things that are not linear. We can do higher order inequalities. And the first thing I want to do with these is factor it. Okay? Now, if this was just equal to 0, then I can see that x is either going to equal negative 2 or x is going to equal negative 3. So those are the interesting values. Those are going to be like the ends of my intervals. But there are a couple of ways to think about this. First of all, I know if something squared is greater than 0, that means I have x times x greater than 0. And this would mean that this have to be positive, or they could both be negative, right? But I can't get a positive times a negative to get a positive. So what this really means is that either x plus 2 is positive and x plus 3 is positive, okay? Or they are both negative. So notice how I use the or and the and statements. Or implies one or the other, but and implies that they both have to be true. Okay, so now I can solve each of these. This tells me x is greater than or equal to negative 2. And this one tells me x is greater than or equal to negative 3. If I put those on a number line, and I want to be greater than both, the and tells me that I have to be here. Okay, because I have to be where they are both true. Okay, now in the bottom one here, this also tells me x with negative 2, but now I'm less than or equal, and x less than or equal to negative 3. If we put those on a number line, notice it's the same number line, negative 3 and negative 2, but now I need to be less than both. So again, because of that and statement, I need where both of them are true. So this tells me x is less than or equal to negative 3. So my solution is x greater than or negative 2 or x less than or equal to negative 3. So on a interval, that would be negative infinity to negative 3, union with negative 2 to infinity. Now, if you need a little help with the set builder and the intervals, I would suggest watching one of my earlier videos on the number system. It'll take you through doing some of those sets. Now, there is an alternate method, okay? And method 2, the method 1 was very algebraic in nature. And regardless of how many factors you have, you can set up all these ands and ors. But method 2 is going to look at it a little more visual. We're going to set up a kind of a chart. So I'm going to start with a number line with these two values of interest on it. And we notice that that breaks the number line up into intervals. So I'm either going from negative infinity to negative 3, I'm going from negative 3 to negative 2, or I'm going from negative 2 to infinity. And then all we're going to do is we're going to test. Okay, so we're going to test some number. So I choose a number. So let's say we choose something between a negative infinity and negative 3. So maybe negative 4. I'm going to choose a number between negative 3 and negative 2. So maybe negative 2.5. And then I choose something bigger than negative 2. So maybe 0. Okay, and then we're going to test those in each of these factors. So x plus 2, x plus 3, and then their product. And you can, once you get practiced at this, jump all the way to testing it in the product. But breaking it out just kind of checks all of our boxes. So if x is negative 4, x plus 2 is going to be negative. If x is negative 2.5, then x plus 2 is also negative. If x is 0, then it's positive. If I do that same test in x plus 3, I get a negative. Oh, sorry, I'm plugging in the wrong number, 2.5. Let me erase that and make it better. So negative 2.5 plus 3, now that's positive. And 0 plus 3 is also positive. Now I'm going to check their product. So I'm going to do a negative times a negative. We're multiplying, so that makes a plus. A negative times a positive would make a negative. Positive times positive makes a plus. Now if I look back at the original, it wanted greater than or equal to 0. So my solution is this one and this one. So that means this interval and this interval. And so the solution is negative infinity to negative 3, union with negative 2 to infinity, the same result we got in method 1. Now method 1 is nice, especially if you only have 2 factors, but as you get bigger and higher in order and you get 3 factors, 4 factors, 5 factors, that's a little bit complicated. It gets complex to sit in with all those ands and ors. So the chart method, method 2, sometimes can be a little simpler because it just keeps everything all lined up. But feel free to practice both ways. So hopefully this makes you feel a little more comfortable solving inequalities. If you're in class with me, we'll be doing a couple more of these higher order inequalities tomorrow that you can see on your worksheet. If you're just online out there with me, feel free to comment below if you've got any questions. But hopefully this helps. We'll see you next time.